Hello everybody, my name is Johanna Heinonen. I come from Nokia Research and I'm going to talk about SDN-based applications in OpenStack. So this talk is about SDN and it's about OpenStack, but it's not about SDN in OpenStack. With this I mean that I'm not going to talk how Neutron is utilizing SDN when it's performing its tasks. Instead of that, this talk is about SDN-based applications in OpenStack. These applications, they are distributed, dynamic, and they utilize neutron networking. So what are these applications? For example, SDN-based IP router. The routing daemon is in the OpenStack cloud, and the distributed forwarding plane is outside the cloud. SDN controller is used to configure the flows to the forwarding plane switches. A little bit more complicated example is 3GPP packet gateway. Here again, the control plane is in the cloud. Distributed user plane is in distributed cloud because of the need for mobile edge computing for certain applications. In addition to this, mobility adds the requirement of dynamic user plane. So if we go a little bit more deeper into virtualized SDN-based router, first of all, the L3 or the IP addresses are in the control plane, which is a routing daemon running in OpenStack virtual machine. In our test setup, this is a Quokka routing daemon. Physical interfaces and packet forwarding is in the user plane, which are Open vSwitch instances. As such, this is a standard IP router with distributed SDN-controlled forwarding plane that is capable of running routing protocols and advertise route updates via its physical interfaces. So it looks simple, but if you think about the OpenStack installation, the routing daemon is in the compute node in the VM, and then there are tenant routers, NATs, floating IPs, and so on. So there comes the problem, how to make the routing daemon see its physical interfaces. Our solution has been that we have installed the Neutron agent to the user plane elements. This way, the user plane elements are connected to the same L2 segment and virtual Neutron network as the routing daemon, and it's possible to send routing updates via physical interfaces. Then the other example about these SDN-based virtualized applications in OpenStack is this packet gateway. It's an essential part of 3GPP network architecture. The other parts are base stations in the radio network and the mobility management entity which handles the mobility management signaling. In the user plane, the mobility is realized between the gateway and the base stations with the user-specific GTP tunnels, which are reconfigured during handovers. So if we have a closer look about this SDN-based virtualized packet gateway, again, the S+P gateway control is in the cloud, but for the user plane, there are several options. For best effort sessions, the user plane in the data center in the virtual machine could be reasonable, for example, for huge amount of machine-to-machine type of sessions. Then in some cases, user plane in dedicated hardware outside cloud could be reasonable, for example, in cases where hardware acceleration or media conversion is required. And then finally, user plane in the network edge is required for latency critical applications. Here we also need computing resources in the network edge. As a conclusion, it can be said that this mobility anchor in the user plane can be selected optimally for each type of mobile equipment. When we built our research prototype, there were many issues we had to solve. First of all, standard OpenFlow protocol is capable of transferring protocol information only in layer 2, 3, and 4, not in layer 7, where the GPRS tunneling information is carried. For these reasons, some extensions to OpenFlow protocol and user plane switches are required in order to enable this mobile-specific tunneling. In OpenStack side, when the user plane switch is in OpenStack virtual machine, first of all, the IP spoofing must be allowed because packets from the UE arrive in the mobile-specific tunnels, and native IP packets to the UEs arrive from the internet to the same interface. Then the user plane virtual machine has one interface, which is a port in the OpenVSwitch instance. Then you have to be careful that you don't cause broadcast storms. This can be the case, for example, if the DHCP is enabled in the related neutron network. And there are also many user plane performance issues in the clouds, but there are many ongoing activities in OpenStack related to these. Then distributed compute nodes located in the network edge, they offer computing resources for latency critical applications. This means that there is a need to have a straight network access to the radio network. And at the same time, the mobility anchor is located in the network edge. So in these elements, actually these distributed compute nodes, they are the neutron network control and the gateway specific control. They need to cooperate. Because of mobility and diverse application requirements, the optimal mobility anchor in the user plane can be maintained only if the tunneling termination point can be switched dynamically. According to the current 3GPP specifications, this is not possible. But if you have this kind of virtualized SDN-based packet gateway, this kind of P-gateway relocation is possible. Because gateway-specific SDN controller is capable of modifying the tunneling termination flows and the related routing in the real time, and on the other hand, Neutron Virtual Networks overlay, it decouples traffic from underlying network infrastructure and addressing, and thus enables relocation without the mobile equipment IP address chains. For example, certain machine-to-machine session might require this feature. In general, most of those, they send a report every now and then, but if one of those starts a motion detection or starts video streaming because of motion detection, it would be reasonable to drop this kind of session, for example, to a special hardware. And also this mobile edge computing and latency critical applications require this kind of dynamic tunnel termination. So in summary, it can be said that distributed and dynamic SDN-based applications in OpenStack Cloud, they utilize Neutron Virtual Networks overlay. For virtualized SDN-based IP router, the overlay provides means for connecting routing daemon to the distributed forwarding elements in layer 2. And for the packet gateway, the overlay gives the possibility to execute the seamless P-gateway relocation procedure. Our research prototype implementation, it uses OpenStack with the following modification. First of all, the Neutron agent is installed to all user plane elements. Then IP spoofing is allowed. And then in the distributed nodes, the Neutron network control and gateway-specific network control need to cooperate. Thank you.